Alright, okay. Hi, hello everybody. Welcome back to another one of these videos. Today, this is actually dedicated to my friend who's going to be missing class for 2 weeks. Um, this is a recap of this week from the 21st to 24th, I think. I know it says 1.19 right there, but this is like an old paper. So yeah. Also, I don't have this paper anymore. Because I turned it in because if I show you here, there's homework. So I had to turn it in. So right now I'm using my teacher's answer key for this one. I don't ever actually like use them though. Anyways, I'm gonna be going over the important stuff that we learned on this day, as well as the next, and all of the ones for this week. Anyways, for right now, the very important thing here on this page is how many radians are in one revolution. This is there's 2 pi radians in revolution, and then the teacher explains right here, like, once you go 1 revolution in a circle, this is 360 degrees. Whoa, it's not 36 degrees, 360 degrees, which is just equal to 2 pi radians. Which, by the way, radians is going to be the new units we're going to be using. Remember that. This was just a demonstration, which we didn't even get into class because we had a short day because of the snow. It was really cold. Anyways, this is what we focus on. Theta is basically going to be our new position measurements for angular problems. So angular position is theta. It's how much something rotates, and the units right here are degrees, revolutions, radians, and rotations. And the teacher pointed out that we use radians the most. So like we're just gonna be writing that as rad radians. Anyways, also, yeah, make sure you know how to convert radians. So to like from anything sorry, excuse me, that was a horrible stutter. Let's say the problem said we had like 1 revolution, right? Make sure you know how to convert this into radians. We already established that it's 2 pi, so it's gonna be 2 pi radians, and then take out 1 rev. So I apologize for that horrendous spelling, not spelling, handwriting. So it's gonna be 2 pi radians. But let's say you had a 360 degrees, and we're gonna do the exact same thing. 2 pi rad over 1 is equal to not over 1. Hold up. Two pi radians. Boom. That's it. Let's say we had a circle with a sensor and a stick attached, and the circle was spun, right? And the stick moved, had a revolution every minute, so 1 RPM. This can be converted to 1 revolution per 1 minute. But we want to have this in radians per second, right? So let's first get rid of the minute. So, oh, okay. Yeah, no, I was making this way harder because it's at the bottom. We actually put minutes at the top, and then divide by seconds, and then we do times 2 pi radians, and then divide by 1 revolution, because revolution's at the top, and so to divide it, we divide it by the bottom. So boom, 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 boom. This equals to 2 pi radians per 60 seconds, which, if you do the math, it's gonna be 2 pi divided by 60, 0.104, and actually I'm just gonna round that up to 5 radians per second. There you go. Anyways, this is angular velocity, and the letter we use for angular velocity is going to be omega, which kind of looks like a W, but it's omega. And average angular velocity will have the equation of delta theta over delta time, which just means change in theta or change in angular position over change in time. And the units we're just going to use for this is radians over seconds, you know, revolutions per minute, which I actually use right there, and degrees over seconds. Anyways, yeah, I'm pretty sure, yeah, like this is where converting becomes important. This is where you're mostly going to do your conversions. Not really that much over here for angular position, but for angular velocity, yes, conversions are really important. Anyways, you can give this a try if you want and calculate the angular velocity of the second hand and the clock. I don't know, you don't really need to. Anyways, I'm going to move on to angular acceleration, which the letter we're going to use is alpha, and it's just drawing like the infinity sign itself. You just take this part out. I took much more than that part out, and just leave a fish. Look, a fish. But yeah, not fishy. Anyways, yeah, that's alpha, and it means change in angular velocity per time. So yeah, average angular acceleration is going to be change in omega over change in time, which also means omega final minus omega initial over change in time. By the way, I'm just saying omega because I don't want to say the entire thing, which is change in angular velocity, so it's very long. But it basically means how much speed of a rotating object increases or decreases per the time interval. By the way, the units we're going to use is radians per second squared, and we really just want to focus on radians per second squared. If we have anything else, I would just recommend to convert over to radians. Anyways, yeah, you can try those, but this is where I want to focus on. You see our linear position, it's x, our linear velocity is v for velocity, and our linear acceleration is a. Now let's go over here to angular. Our angular position is theta, our angular velocity is omega, and our angular acceleration is alpha. And basically, this is super important. Just like how we have constant acceleration equations for linear terms, we're also going to have constant angular equations, which are going to be the exact same thing for their respective units. So let's say we have velocity final is equal to velocity initial plus acceleration times change in time. Now we have angular velocity final is equal to angular velocity initial plus angular acceleration times change in time. These are going to be similar, except it's just what's called going to be with the angular terms. Also, thank you, teacher, but yes, be careful with units. Sometimes you're gonna be messed up, and there's gonna be like different units. Like maybe this might be in like RPM, and then this is in like radians. So make sure you convert them all to the exact same unit. And I really recommend using radians because we're gonna be talking about something later. I don't know if it's today, on this day. No, it's not this day, but in a future lesson, the teacher really goes into. Sorry, not the teacher. In a future lesson, we talk about some certain things that can only be used if the equation is in radians, or like what's given is in radians. Anyways, let's go into the homework. This is just for my friend at this point, and if you want to do some practice, you can do this along with me. A wheel rotates 3 times. Through what angular displacement radians does the wheel rotate? So the wheel rotates 3 times. That means it just went through 3 revolutions, right? And we already established that a revolution is 2 pi and in radians. So 3 times 2 pi is equal to 6 pi radians. And that's it. And now let's move on to the second one. Through what angular displacement in radians does the Earth turn in 24 hours? All right. 24 hours, the Earth has a full turn. So that means it's just 1 revolution, which just means it's just 2 pi radians. There we go. That's it. Good job. Let's move on to this one. Determine the angular speed in radians per second of Earth about its axis, the minute hand of a clock, and egg beater turning at 300. Okay. Sure. Anyways, for A, we said it's 1 revolution per 24 hours. So let's multiply by 1 minute. Sorry, not multiply by a minute. Whoa, calm down, guys. We're actually gonna divide. Sorry, we're gonna multiply by an hour, and then there's 60 minutes in an hour, so 60 minutes. But we want it in radians per second. So once again, we're gonna multiply by a minute, and then divide by seconds, and then we multiply by 2 pi radians. That says radians, I promise, and then divide by 1 revolution. So this should be pull out your trusty calculators. 2 pi divided by, and I'm just not gonna do that. There we go. This should equal to, Jesus. Okay, sorry. 7.272 e to negative 5. Let me just go check if that's correct. Yup. Oh, I forgot my units. Come on, guys. Don't forget your units. Units are very important. Radians per second. By the way, E is just 10 to the power of this big E, not little e. That's a whole different thing. But yeah, there's your answer. Now let's move on to B. The minute hand of a clock. Oh man, okay. It has 1 revolution per 1 minute. So we're gonna multiply by a minute, divide by 60 seconds, and then 2 pi rad over 1 rev. And then that's gonna be 2 pi divided by 60, 0.104. Right? Ooh, I messed up really badly. Okay, where did I go wrong? Okay, I was wrong. This is actually the second hand. The minute hand actually does 1 revolution in an hour. So 1 rev over 1 hour. Let's convert this into minutes. So 60 minutes. And then let's convert that into seconds. So 60 seconds. And then let's convert this into radians. Rad over 1 rev. And then this equals to, let's see this. 0.0017, and I'm gonna round up rad per second, which should be correct now that I didn't make that silly mistake. Yup, good job. Which means I apologize for what I said at the very beginning here. This is actually the second hand. My bad, guys. My bad. My apologies. Anyways, let's do an egg beater. I don't even know what the heck that is. Is that do they mean like the whisk? Anyways, an egg beater turning at 300 revolutions per minute. So 300 rev per minute. Let's first turn this into radians, and then which you don't really have to do this in an order. You can just do it whenever, however you want it to. 300 pi. Sorry, 600 pi. Divided by 60. It should just be 100 pi, which is a 31.416 radians per second. Let's see if that's true. Yup. Although the teacher rounded up. Well, rounded. Yeah, I can't even say words. The teacher rounded right here. Anyways, a compact disc's rotation varies from about 200 to 500 RPM. A disc plays for 74 minutes. What's its average angular acceleration in A, RPMs over S, or B, radians per second squared? Okay. So let's assume this is our angular velocity initial, and this is our angular velocity final. Sorry, I wrote initial again. Final. All right, so let's write down what's given. It's equal to 200 RPM. Our angular final is equal to 500 RPM. Our change in time is equal to 74 minutes. And we want to find average angular acceleration. All right. So the first, they want us to find it in revolutions per minute per second. So we're going to keep this the same, but this we're just going to convert to seconds. So 74 minutes times 1 minute divided by 60 seconds is equal to... Wait, sorry. I reversed it. It's actually supposed to be times 60 seconds divided by 1 minute. 4,440 seconds. All right. Now let's use our angular velocity, our angular acceleration equations, which I really recommend you memorize. In this case, we have a change in time, so I'm just going to be using WF is equal to WI plus A change in time. Not A. This isn't linear. Alpha. And we have 500 is equal to 200 plus alpha over... Wait a minute. I actually don't need to use this. My bad, guys. I'm doing too much work. This is a average acceleration. Don't use your I am so sorry, guys. Do not use your constant angular acceleration equations for this, because it doesn't state that our acceleration is constant. It states that we're going to have an average one, which means it's going to change at some point. So do not use them. This is when our acceleration is constant. So instead, we're actually going to use 500 minus 200, because WF minus WI over change in time. So over 4,440 seconds, which means we're going to get 300 divided by 440, 0.0676 RPM per second, right? Yeah, I just didn't round until later, but yeah, boom. Now let's solve part B, where we're gonna actually move this and change it to radians per second. So 200 rev per 1 minute, it's gonna be 200 times 2 pi divided by 60. And then we're going to do the exact same things for the other one. So 500 times 2 pi divided by 60. 52.35. Sorry. 35. Actually, let's just round it up to 36 radians per second. Anyways, this is where I really recommend you just use a calculator and input these in. So let's do this. Minus 20. And then divide by 4440. Let's see if that's correct. Yep, okay, it is correct. I just wanted to make sure first. So 52.36. I didn't actually use these numbers. I used the exact number the calculator gave me. I really recommend you guys do that too. But this gives around 0.007 radians per second squared. All right, remember that's squared. Radians per second is just radians per second squared. There you go. That's how you solve that one. The rotating blade of a blender turns with constant acceleration. this is when we start using those constant acceleration equations. Constant angular acceleration 1.5 radians per second squared. How much time does it take to reach an angular velocity of 36.0 radians per second? So this lets me know this is WF, and I'm gonna assume, oh yeah, it says right here, from rest. So WI is just equal to 0 radians per second. Radians per second. Through how many revolutions does a blade turn in this time interval? So first, A, we want to find our change in time. So let's write down what's given to us. Alpha is equal to 1.5 radians per second squared. WF, it's equal to, what was it? 36. 36 radians per second. Also, I'm pretty sure I just called it WF. It's omega F. And then WI is equal to 0 radians per second. Omega I. And we want to find change in time as well as change in theta. But first, let's go with change in times, and that's part A. So this is when we finally use that equation that I was saying before. Omega F is equal to omega I plus alpha change in time. So now we can actually plug this in. 36 is equal to 0 plus 1.5 change in time divided by 1.5 divided by 1.5. And then I'm going to use the calculator for this because I'm not good at mental math when it comes to decimals. Change in time is equal to 24. Sorry, 24 radians, right? Because we're in radians. Let's check that out if that's true. My bad. 24 seconds. Because how is change in time in radians? My apologies. But yes, that is true. V, sorry, not V. B is now what I was actually trying to figure out here. So we could use either one. I would prefer to use actually, let's test that out. Let me show you this. All right, WF squared is equal to WI. Whoa, that is not a W. WI squared plus 2 alpha change in theta. Let's see if this would actually give me the exact same answer. So we said this is a 36 squared is equal to, and 0 squared is just 0. 2 times 1.5 times change in theta. Let's divide by 2 times 1.5. 36 squared is going to be 1296. Divide this by 2 times 1.5, which is just 3. Change in theta should equal to 432 radians. Now let's see if this is true. By using this equation, change in theta is equal to WI, change in time, plus 1/2 alpha change in time squared. All right. So since omega initial is 0, we're just going to focus on 1/2 times 1.5 times 24 squared. So 24 squared is 576 times 1.5 is 864. Divide this by 2 is 432. So let's write that down. 1/2 times 1.5 times 576. 1/2 times 864, which is equal to 432 radians. See, both will give you the exact same number. And let's check that out if that is true. My apologies, guys. I do not know where I read. Wait, hold up. Okay. Sorry. I just need to convert this into revolutions. So 432 radians over 1 is just going to equal to, we're going to divide this by 2 pi radians, 1 rev. And this should equal our actual answer that is on the answer key, right? 432 divided by 2 pi. I'm gonna round it. 68.755 revolutions, right? Or like somewhere around there. 68.7 revolutions. Yes, thank you. My bad, guys. I forgot to convert to revolutions. But yeah, see, this is an example where you need to convert. Anyways, yeah. An ice skater going into spin rotates with an angular velocity of 27 radians per second. How many revolutions will the skater make each second? So, angular velocity, 27 radians per second. We want to convert this into revolutions. So it's just going to be 27 radians over 1 second. Times 1 rev, divided by 2 pi. Whoa, that's not a pi. That's an R. Or a V, I don't even know. 2 pi rad is equal to 27. 27 divided by 2 pi. Also remember, in your calculators, when you're doing divided by 2 pi, make sure to put a parentheses around 2 make sure to put a parentheses around 2 pi. Or else it's just going to do 27 divided by 2, then multiply by pi. This should equal to 4.297 revolutions per second. Right? Yep, we're correct. Anyways, there you go. That's the homework done for this one. Let's move on to day 1.22, which I actually don't have. But the most important thing right here is this part. We know that in linear, and this one very important thing, only applies when units are radians. All right, this only applies when units are radians. We know that instantaneous velocity is dx over dt. So omega is going to be d theta over dt. This means instantaneous angular velocity. All right, not a parentheses. Come on, there we go. Instantaneous angular velocity, and the exact same pattern is going to apply to alpha, which is equal to dv, not dv, sorry, d omega over dt, which means instantaneous angular acceleration, which just means acceleration at like that one point. All right. Yeah, so instantaneous angular acceleration. Same thing applies here with the average velocity and average acceleration. So over here, where average velocity is change in x over change in time, and here, average angular velocity is going to be equal to change in theta over change in time. I'm not going to write that one out. You can write it out, but oh yeah, which is going to just equal to theta f minus theta I over change in time. Average angular acceleration. It's the exact same thing, but it's change in omega over change in time, which is equal to omega f minus omega I over change in time. There you go. That was the most important thing of this day. You can let's skip all the way over to the homework, which actually first we need to learn one thing, because there's a big note right here that says wait until after class 1.23 to do certain problems. So let's go to 1.23. All right, this paper, I think I have, yeah, I have this. All right, very important notes here to do. Okay, we're gonna relate linear and angular kinematics. All right, so here we have a circle. Here, whoa, what did I do there? Okay, here we have our r, or radius, and then this is going to be how much our displacement and theta is going to be. But this part right here, this part is going to be our arc, not, well, our arc length. All right, there's an equation for this in calculus, but right now we're going to focus on the equation for here in physics. So arc length in physics specifically relating to angular terms. We know this. If theta is in radians. Actually, my apologies, guys. This is the one that has to be in radians. The other one doesn't have to be in radians. This one can be whenever. But I mean, I'm not gonna erase it because I really do recommend you just change it over to radians. Radians is much more used. Anyways, if theta is in radians, then x, our linear position, is equal to a radius times theta. All right. So now let's figure out what is velocity equal to. Well, we know that velocity is equal to dx over dt. So here we have x is equal to r theta. Let's take the derivative of this. So dx over dt is equal to d over dt, the derivative in respect to time of r times theta. So v is equal to, and r is just a constant, all right? So this is going to be the same, r times d theta over dt. And remember what we established earlier, that a d theta, hold on, let me go back. What was it, this far back? That d theta over dt is omega. So v, our linear velocity, is going to equals radius times omega. And now that you notice that pattern, what do you think a is equal to? Well, if we do the exact same thing, where dv over dt, because a is equal to a dv over dt, and we take the derivative of r times omega, we get that a is equal to r times times alpha. Wow, isn't that astonishing? So let's put them all right here. X is equal to r theta, v is equal to r omega, and a is equal to r alpha. Wow, this is a very key thing to pick up on today. Well, like this day. So now let's go back to the homework. Let's put all of this that we learned into use. So here we have angular precision equation. Theta t is equal to t to the power of 4 divided by 4 minus 2t. Determine the angular velocity of the disk at t equals 2 seconds. So we know that d theta over dt is equal to omega. So omega, the omega key, the omega equation for this problem is going to be omega cubed minus 2. So that's just going to be 8 minus 2, which is equal to 6 radians per second. Whoa. 6 radians per second. Let's make sure we were correct, right? 1. Oh, wait. Where are we? 1c. There we go. 1c. Boom. Right, we were correct. Determine the angular acceleration of the disk at t equals 3 seconds. So alpha is just the derivative of omega, so this means it's going to be 3. Hold up, guys. I made a mistake right here. This is supposed to be time. 3t squared. Hold up. Okay. Alpha. Yeah. Sorry, I actually don't know what to call this. I'm just gonna call it alpha equation, even though it's not the alpha equation. Like, yeah. Our acceleration equation right now is 3t. Sorry, our angular acceleration equation right now is t. Our angular acceleration equation right now is 3t squared. Yeah, and that's it. So and this is when the time is 3 seconds. So 3 squared is 9, and 3 times 9 is 27 radians per second squared. Let's check that out. So that was B. Yeah, 2 is B. There we go, we're correct. This is where we needed the info from day 1.23. So determine the linear speed of a point on the disk 50 centimeters from the center at t equals 1 second. So r is equal to 0.5 meters, and we are looking for v when we know it's 1 second. So let's find wt. Omega t is, once again, t cubed minus 2. So w omega at 1 second is just 1 minus 2, which is equal to -1 radians per second. So our linear velocity is equal to r times omega, which means our linear velocity is equal to 0.5 times -1, which is equal to -0.5 radians per second. Oh, sorry, not radians, because we switched over to a linear. 0.5 meters per second. -0.5 meters per second. Let's check that out. We said that was A, and yes, it's A. So good job, guys. We did it. Let's go on to the next problem. A bicycle has wheels with radius 50 centimeters. The bike starts from rest, and the wheels speed up uniformly to 200 revolutions per minute in 10 seconds. How far does the bike go? Through how many revolutions does the bike wheel rotate? Okay, it's 200. Wait, it starts from rest. Oh man. Okay. For part A, we're gonna have to use our constant angular acceleration equations, right? I'm gonna assume. Yeah. So our Wi is equal to 0. Wf is equal to 200 RPM. So let's use that equation. Change in time is equal to 10 seconds. We know that Wf is equal to Wi plus alpha, change in time. So that means that 200, and I'm actually gonna just first convert this to a radians per second. So this is 200 rep per 1 minute divided by 60 seconds, multiplied by 2 pi rad for 1 rev, which is going to be 400 pi. Divide this by 60. 20.944 radians per second. So now let's plug this in. I'm just going to call this A. A squared is equal to 0 plus alpha times 10 seconds. So then we just divide by 10 of A squared. And let's make sure this is actually correct first, because I don't want to make a mistake. Oh, it's in revolutions. I did. How many revolutions? My bad, guys. I didn't actually need to convert into radians. So 200 divided by 60 seconds. This is going to be 3.333 reps. And let's call this A. So A squared is equal to 0 plus alpha, change in time, which our change in time is just 10. And then square this, divide by 10. Ooh, is that true? No, I messed up. Sorry, no, I didn't mess up. Because right now, I solved for alpha, which isn't how many revolutions it goes. So this is alpha revolutions per second squared, I'm pretty sure. So now let's actually solve for theta. So let's remember, change in theta is equal to Wi, change in time, plus 1/2 alpha, change in time. squared. And I know this looks like a lot of steps, but yeah, this is a lot of steps. Anyways, WI, we already established is 0, so this is going to be 1/2. Now let's plug in our alpha. Change in time, squared is just going to be 100. So, and 100 times 1/2 is just 50. Let's do 50 divided by this. I messed up once again. Hold up, guys. Oh man, this is pathetic. First, let's just start off by changing this to 200 revs per minute to 60 seconds. So 1 minute 60 seconds. So this is 200 divided by 60 rev per seconds. 10 seconds. So let's say 200 divided by 60 divided by 10, 0.333, and then 0.333. Let's say this is our acceleration, right? And let's assume it's going to be constant. So we're just going to use this in our change in theta equation. And let's plug in what's given. First part is going to be 0 plus 1/2, and then this is 0.333. So 0.333 times and 100. Sorry, 10 squared is just 100. And this should give you an answer of 16.667 radians, not radians, revolutions. Which, let's check if that's correct now. 16.8. Yeah, sure, whatever. I'm assuming that's how we got to this answer. Anyways, how far in meters does the bike wheel go? So, we know that the linear position equation in relating it to angular kinematics is r theta. And theta, we just figured it out, and we said that we can only use those equations when it's in radians. So let's just multiply by 2 pi, which means this is going to be 104.71. Oh, 72, because we can round that up radians. So x is equal to 0.5 because we established that it was 50 centimeters away from the center. So 0.5 times, well, like the wheels. The wheel's radius is 0.5. My apologies. 104.72. So let's do that, and we should get a linear position of 52.35. Actually, we can just round that up to a 36.36 meters. That's how far the bike wheel goes, right? Yeah, 52 point, or although the teacher got 86. I don't really mind though. During the spin-dry cycle of a washing machine, the motor slows from 95 radians per second to 30 radians per second, while turning the drum through an angle of 402 radians. What is the magnitude of the angular acceleration of the motor? So this is when we actually are supposed to use the angular acceleration equations. I think. I'm pretty sure. I don't know if it was a right choice for me to use them right here, but it gave me a similar enough answer, which is why I kept mine as that when I did the homework. We'll see though. Anyways, so this is WI and this is WF, which means the magnitude. Yeah, okay. The direction would be negative, but the magnitude doesn't matter. Triangle 402 radius is just theta. So yeah, we're trying to find what alpha is, and the perfect equation for that, given what's given to us, is this. So WF is 30, and then we're going to square that, and then we have WI, which is 95, square that, plus 2 alpha, and then change in theta, that's change in theta, 402. So just pull out your trusty calculators. 30 squared is 900. I don't know how I couldn't have done that in my head. It's so obvious. 95 squared is 90, 25, not 90 and then 25, 9,025, plus 2 alpha, 42, which is shit. Let me just rewrite that as 804, plus 804 alpha. So then we subtract 9,025 from 900. So this is going to be negative 8,125. It's equal to 804 alpha. And then let's just divide by 804. Divide by 804. And we get alpha is equal to negative 10.10. 6 radians per second squared. Our magnitude is just the number. And what is the one on here that is the most equal to 10.106? Actually, hold up. I want to check something out. What happens if we used alpha, average alpha? Oh, we actually wouldn't be able to because we don't have change in time. Never mind. So yeah, the closest answer is C, 10 radians per second, which, let's look at that, 5 is equal to C. All right, yep, nice job. Excuse me. Let's look at problem 6. It's given by, okay, we want to calculate the angular acceleration of the wheel as a function of time. So omega is a function of time. In this equation, it's going to be the derivative, so 2bt minus 3ct squared. This, and then we're going to find alpha, which is going to be 2t minus 6ct. Let's see that. Yeah, we got it. At what time is the angular velocity of the wheel instantaneously not changing? So instantaneously not changing. So when the acceleration is equal to 0, so 2 minus 6c. Sorry, 2bt minus 6c. So 6c is equal to 2b divided by 6c divided by 6c. It's not changing. When it's b over 3c. Yeah, got that correct as well. Sorry, I'm really tired right now. If you look at my iPad time, it's 10:52 p.m. What it means by like angular velocity is not changing at that exact same that exact second. I think it means like instead of like this point right here, like it goes from increasing to decreasing, which at this point in the derivative it would look like this, where acceleration is going to change at a 0, which is why I used 0 equals to our acceleration function, which was 2vt, because that's when a velocity is going to change. Anyways, and that's like as in simple terms. I don't even know if I actually said it correctly, but you hopefully understand what I meant. Anyways, let's move on to 7. A cyclist is traveling at 7.0 meters per second to the right when she applies the brakes and slows down to a speed of 5.0 meters per second. Each wheel of the bicycle has a radius 0.33 and completes 5 revolutions during this braking period. Determine the angular acceleration of each wheel. So, oh my goodness. Okay. Let's change this to a radians. 10 pi radians. Okay. Let's see. We are given VI and VF. So VI, let's use a... Actually, we can't use that. Hold up. I forgot what I did for this. Let me try something. I'm not going to add that much commentary because I'm going to try something. What are we looking for again? Silly me, I'm getting tricked here. Okay. 10 pi. All right. X is equal to 10 pi 0.33. Oh my goodness, I'm getting tricked again. Hold up. Wow, hold up, guys. I am so tired. I need to figure out what the heck I'm doing. My bad. I accidentally stopped recording. This looks like a really fun problem because it's making you use everything that you learned. So x is equal to 3.3 pi. Anyways, now let's find for acceleration. Vf squared, which is, let's see, 5. So 25 is equal to Vi squared, which is 49, plus 2 times alpha, wait, sorry, not alpha, 2 times acceleration, because we're using linear terms, times 3.3 pi. So let's subtract 49 from 25. This should just be negative 24, right? Yeah, negative 24 is equal to 2. Yeah, see, I accidentally stopped recording on accident. 2a 3 point. I'm just gonna write this as 6.6 pi a divided by 6.6 pi by 6.6 pi. So divided by 6.6 pi, I get acceleration, linear acceleration. Linear acceleration to be 11.424 radians per second squared, right? Did I use radians? Yeah, I did use radians. I'm actually not sure if this is the answer because the answer is in here. Wait, it is. Hold up. Never mind. I messed up really badly somewhere. Where did I mess up? 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 I messed up really badly somewhere. Hold up. Where did I mess up? Hold up. Whoa, 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 whoa. I messed up somewhere. Okay. Remember what I said earlier, where when you divide by number and then pi, you have to divide with that in parentheses? So, let's divide 24 again by parentheses 6.6 pi. Now I get the answer I want. This is going to be negative 1.15 7 radians per second squared, which our teacher just simplified to sorry guys, I forgot this is acceleration, so that it's gonna be meters per second squared. I made two horrendous mistakes, guys. Remember to put parentheses. Anyways, knowing that a is equal to r alpha, and we know that this is our a, and that this, not that, hold up, this is our radians. So divided by radians, alpha is just equal to a divided by r. So 1.15, well, negative 1.15 divided by 0.33 is going to give us 3.507 radians per second, negative 3.5 radians per second squared, which, yep, we got it. We got that correct. Anyways, nice job, guys. Last question. A satellite experiences a gravitational force of 228 newtons. Well, I know that the mass of Earth is 5.97 E24. That's the only thing I memorized. I don't remember the radius, which I'll write that down later. Anyways, we know that this distance is 4E7. And we know that F of G is equal to G times M1, M2 over R squared. So F of G, is equal to 6.67 e to the times M1, M2. Let me look at my equation sheet for the radius of the Earth. Hold up, guys. This might take a while because I don't have it memorized. Okay, here it is. Radius of the Earth is 6.38 e to the 6. 6.38 e6. But this radius also takes into account 4e7. So 4e7. And this is equal to f of g. And f of g is given to us 228. Now I'm going to be really lazy here. And I'm just going to separate these two. So I'm going to divide by, and I'm going to call all of this a. Because I don't actually want to write all of that. Divide by a. So divide by a. And 228 divided by a should equal to m2, which is the mass of the satellite. And so 228, and I just need to actually write all of this down into a calculator now. 228 divided by 6.67 e negative 11 times 5.87 E24. That divided by 6.38 E6 plus 4 E7. And that should all... Where did I mess up? Oh my god. Hold up. I know where I messed up. Sorry, it took me a few seconds. I forgot to square that. So let me go back in my equation that I put down on my calculator, square that, and you should get around 1,231.675 kilograms for your satellite, which the thing closest on here is D, and that's the answer. Good job, people. We did it. Anyways, let's go on to this last day. I hope so. This is the last day. Last day on here. Oh man. Inertia is the resistance to changes in motion. Yup. Sorry, I'm checking the paper right now to see what Okay. I see. These are just fun problems you can do if you want to. I mean, yeah, let's go ahead. Let's do them. Why not? As I said, inertia is resistance to changes in motion. Finding instantaneous angular acceleration at 3 seconds. So we know that instantaneous angular velocity is equal to 2 plus 4t squared. So that means that instantaneous angular acceleration is equal to 8t, which at 3 seconds is just going to be 24 radians per second squared. I'm assuming, because this has to be in radians per second, right? Yeah. Yeah, radians per second. Anyways, find the average angular acceleration between 0 and 3. So now we just need to plug in 0 into this, which is going to be 2, and then plug in 3 into that, which is going to be 2 plus 9 times 4, 36, which is equal to 38. And then that means alpha is equal to change in omega over change in time. So this is equal to 38 minus 2 over 3, which is equal to 36 over 3, which is equal to 12 radians per second squared. And then C, find instantaneous angular speed at t equals 2 seconds. You know that V is equal to R times W, and W2 is equal to 2 plus 16, which is equal to 18. And then R, what was R? 0.8. So V is 0.8 times 18, which is... Oh, My apologies. This is angular speed. Okay, this is angular speed. This is angular. Sorry. This. How do I move this? Is there any way to move this? Yep. Hold on. Right there. This goes down here for the linear speed, which is equal to also. You can barely tell. That's an 18. This is 18. And this equals to 14.4 meters per second. Find instantaneous tangential acceleration at t equals 3. So alpha 3, I'm pretty sure we just said it's a, yeah, so this is a, oh, wait. Yeah, well, 24. And then the tangential just means linear. So a is equal to a 0.8 times 24, which is equal to 19.2 meters per second squared. Good job. This is correct. Can we use the equation? No, because acceleration isn't constant. Also, yes, I know that looks like I said because that looks even worse. Anyways, also, we can't even use this at all because this is for change in theta, so this has to be wi, and then this has to be alpha, and that actually stays the same. Anyways, moving on. This is where things get really important, all right? I'm going to be talking here for a little while. Which stick / mass combo is the easiest to spin? Now, the center mass is going to be the exact same on all of them. It's actually harder here. Then this is a middle. And this is easiest, all right? What might affect how easy or hard these sticks are able to spin? It's where the mass is located. So, where the mass is located. Since when it's located far away, it's harder, but when it's closer, it's easier, and when there's no mass at all, it's just easier. Whoa. So this is where we learn about moments of inertia, going back to the equation, not the equation, the question on do now. This is also called rotational inertia. And the definition is, let me write this down. Resistance to changes in rotational motion. And it's, I don't know why I wrote this part. It's a property of an object about an axis. I wrote this down from the board. I forgot what that meant in here. Maybe I'll remember later and I'll go back to it. But anyways, what this means is that higher amount of inertia is equals to harder to rotate. So let's figure out the equation of point masses. Equation of point masses. Jeez, can this thing really recognize my handwriting? Equation of point masses. Come on, man. That's just masses. Which is, point masses are just small points in space. That's a space. There we go. And the equation we're going to use is I is equal to sigma from I equals 1 to I equals n, or like the sum of m I ri squared, where m is equal to our mass in kilograms and r is equal to distance of object to our pivot, which is in meters. And as in a representation of what this means, this just means m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus dot 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 plus n rn not cubed squared. And the units for I is going to be kilograms times meters squared. So this is very important. This equation is very important because it's solely what we're going to do for the rest of this entire thing. I hate this. Hold up, guys. Let me take a breather. Okay, I'm back. All right. Let's say we have these scenarios. All right. Let's calculate the moment of inertia of each object below, assuming that our pivot is here for this one and here for that one. Now, how do you find R? Now, I know it looks like a lot at first, and it kind of is, but no, not really. Let's break this into this rectangle into 4 smaller rectangles. That's as much as I could. And then let's break these rectangles into triangles. These are just right triangles, and we know that we can use the Pythagorean theorem for right triangles. So we have 1 meter on this side because there's 2 meters in total, and then 0.5 meters on that side, which means that our hypotenuse, and knowing that a squared plus b squared is equal to c squared, our hypotenuse is going to be 1 squared plus 0.5 squared, and cube root all of that, which is equal to c, which is going to be equal to, what did I write? Actually, don't even try and like solve it. Just put square root of 1.25. That's going to help you way on later on because you don't want to write a bunch of decimals. Anyways, knowing this, and that this radius is going to apply on every single one. So R1 is equal to R2, which is equal to R3, just for this one, all right? Then I is equal to, and we can just pick off any one. Let's say 2 is M1. So 2 times the square root of 1.25 squared, which this is just 1.25. So knowing that, let's just do 1.25 plus 4 times 1.25 times 1.25, and because we actually have two of the same, we're just gonna do 2 times 1.25 plus 4 times 1.25, which, let's plug this into our calculator, guys. 2 and then parentheses 2 and then another parentheses 1.25, and then close the parentheses plus 4 times another parentheses 1.25, and then another parentheses to close off the final one. This should equal to 15 kilograms per meter squared. There we go. This one was actually quite easy because our radius was the exact same. Anyways, now let's move on to this one where the pivot point is right here. Since the pivot point is in the center of our mass, for this one, radius equals 0, so we're just not going to count it. Anyways, well, we can. It's going to be 2 times 0, and then for this fourth one right here, the radius is just going to be, or like distance is going to be 1 meter squared, and then once again we're going to have to use Pythagorean theorem again. Sorry, let me turn that off. There we go. The Pythagorean theorem again. 1 squared plus 2 squared is just going to be 1 plus 4, and then square that is going to be square root of 5. So plus 4, and then square root of 5 squared is just 5. And then plus 2 times 2 squared, which is just 4. So it's going to be 0 plus 4 plus 20 plus 8, which is equal to 32. That kind of looks like a 5. Let me fix this. 32 kilograms per meters squared. Nice job, you did it. Here's some more practice that you can do if you guys want to. I'm not gonna, because I really want to move on. Anyways, these equations are gonna be important too. Well, actually, not just those two. All of these equations are gonna be important for some problems, especially for these. So I really recommend you just take a look at these. You know, maybe screenshot them, and then let's try out one of these problems. Let's try number 3. All right. A thin rod of mass 6 kilograms and like 5 meters rotated about its end. For the end ones, we're going to use 1/3 times L squared, which in this case is 1/3 times 6 times 25, which is equal to 2 times 25, which is equal to 50 kilograms per meter squared. Nice job. There we go. Really, you just got to memorize the equations. Anyways, for this, let's say an athlete holds a 3 kilogram small weight. You can do a little drawing where like, that's like his hand, and then this is him holding the small weight. Wait, hold up. Right, and then it's just a little stick man. Anyways, his arm 70 centimeters long and 4 kilograms. So this is 4 kg, and it's 0.7 meters. And the small weight is 3 kg. What is the moment of inertia of the system? I is going to equal to, and then this is where we use our equations plus just the normal moment of inertia equation. So, well, what do we say? Oh yeah, our pivot point is right here. So, we're gonna use the one equation where it's this plus 4, and then our radius is 0.7, well, our length, and then we're gonna add the weight, and our equation was 7 times 0.7 squared. Sorry, not 7, because the weight has a mass of 3 kilograms. So once we add all of this, we're just going to get 4/3 times 0.7 squared plus 3 times 0.7 squared, which is going to get us around 2.123 kilograms per meter squared. There we go. See, this is how we apply this to like actual like real life and stuff. Anyways, I'm not going to do the other one. You can do it if you want to. I'm just going to move on straight into the homework. Here we have our pivot point, which is right there. Find the moment of inertia of the object below. So this is a thin rod, and it's going to be at the end. So remember the equation for that one's 1/3, 0.8, because 80 centimeters is 0.8 meters. Whoa, sorry. Whoa, that's not what I meant to do. It's actually first the mass, and then the meter, 0.8 squared, plus, and then here's our little thingy. Now this is equal to 0.5 kg. So 0.5 times 0.8 squared which is going to be around 0.747 kilograms per meter squared once you put that into a calculator. Yeah, and I didn't just do this off the top of my head. I have my paper right here because this is due Monday. Anyways, let's rank this in order from largest to smallest moments of inertia. So when it's largest, it's going to be hardest to do. This one right here is hard because not only do you have like where the pivot point is at the end, but then you also have extra mass. So that's going to be the hardest. This one is going to be the second hardest because the pivot point is still at the end. It's just that this is like closer to the middle. All right. Third one to be the hardest is it's this one because this is like the pivot point is like right here. So this is still an end. While this one, the pivot point is like in the middle, so these ones aren't ends and they're easier to hold. So this one's gonna be the third hardest. That's C, and this leaves this to be the easiest to do. Anyways, a cube of mass m slides without friction at speed v naught. It undergoes a perfectly inelastic collision with the bottom tip of a rod. I forgot what that one meant. Remind me in the comments if anybody remembers some. With the bottom tip of a rod of length d and mass m equals 2m. The rod is pivoted about a frictionless axle. What the heck? Axle through its center and initially hangs straight down and is at rest. What is the moment of inertia of the cube / rod after the collision? So, that's not what I meant. Okay. It's going to be this, all right? And the pivot point is right there. So, our equation for the thin rod when it's like that, it's going to be 112 L squared. So 112 times 2m times d squared, and then plus the little thingy right there, m, and then because d is like this entire thing, but with m it's only going to be down here, it's going to be d over 2 squared. So this is going to be 16m d squared plus m d over 2 squared. But we want this all to be in the right, what's it called, in the same, the denominator. So let's multiply this by 6 out of 6, and then let's multiply this by 2 out of 2. This can be 212 md squared plus 612. Is this how I did it? Oh wait, hold on. I forgot one part. D over 2 squared is going to be d squared over 4. So then let's multiply this by 3. 212 plus 3 over 12 md squared. And add those together. This is just going to be 5 over 12 md squared. Good job. And by the way, if yeah, there we go. That is confirmation. A 100-gram ball and a 200-gram ball are connected by a 30-centimeter long massless rigid rod. So let's visualize this. This is 100 G, which I'm just going to write as 0.1 kg. They're connected. 0.2 kg. This is a 0.3. The ball rotates about a center of mass. Whoa, excuse me. So the center of mass is right there. I is equal to 0.2 times 1.5 squared, because the distance from here to here is Sorry, not 1.5. Let me change there real quickly. 0.15. So there we go. Plus 0.1 times 0.15 squared. Let me look at my paper. Yep, okay. If we put that into a calculator, you get 0.00675 kilograms per meter squared. Did I have my kilograms per meter squared around there? I don't think I had to in that one. Anyways. Let's move on to number 5. We're back to angular precision. Nice job, people. Okay. The angular precision of a point on the rim of a rotating wheel is given by theta t equals 4t minus 3t squared plus t cubed, where theta is in radians and t is in seconds. What are the instantaneous angular velocities at t equals 2 seconds and t equals 4 seconds? What is the average angular acceleration for the time interval that begins at t equals 2 seconds and ends at t equals 4 seconds? What are the instantaneous angular accelerations d at the beginning and e at the end of the time interval? All right. So A is just asking for instantaneous angular velocity. All right. So theta is given to us to be 4t minus 3t squared plus t cubed. That means, theta t. Omega t is equal to 4 minus 6t. What the hell did I write here? Hold up. Oh, plus t cubed plus 3t squared. So what was it? At t equals 2 seconds. So omega at t equals 2 seconds is equal to 5 minus 12. No, wait. So, sorry. Yeah, hold up. Sorry, my bad. Here, I'm going to make this easier for me. I'm going to write my t's like that. Boom. There you go. So minus 12 plus 2 squared 4 plus 12. This is just going to be equal 4 radians per second. Boom. And this is part A. Now let's go to part B. Let me write this like this. All right, part B. At t equals 4 seconds. So omega 4 is going to be 4 minus 6 times 4, 24, plus 4 times 4, 16, times 3, 48. Negative 20 plus 48. This is just equal to 28 radians per second. Good job. C is going to be, what is the average angular acceleration? Okay. T equals 2, so it's going to be, which means 28 minus 4 over 2, 24 over 2, which is equal to 12 radians per second squared. And then D, what are the instantaneous angular accelerations at D at the beginning? So omega was that. That means alpha t is equal to 4 minus 6 plus 6t. So, wait a minute. Oh yeah, at the beginning of the interval. So alpha 2 is equal to 4 minus 6 plus 12. Negative 2 plus, okay, this is just equal to, wait, sorry. One big mistake. The derivative of constant is 0, so I don't count that for. It's just going to be negative 6 plus 6t. So this is going to be negative 6 plus 12, which is leads this to be 6 radians per second squared. Boom. And then last part E, omega 4 is equal to negative 6 plus 6 plus 24, which 24 minus 6 is 18 radians per second squared. Good job, guys. We did it. This is where I was actually at. So now I'm going to be doing this one along with you. Okay. A disk initially rotating at 120 radians per second is slowed down with a constant angular acceleration of magnitude 4 radians per second squared. constant is a big key word right there. Stop. WF is equal to 0. So WI is equal to 120 radians per second. Alpha, we said, was 4 radians per second squared. WF is equal to 0. How much time does the disk? Okay, we were looking for time. So, and this one's just should be basic knowledge by now. WF, not squared, is equal to WI plus alpha, change in time. So WF is equal to 0. We said WI is equal to 120 plus 4 times change in time. So, oh, and also negative 4. Because, where did we say? Slowing down, and this is a positive value. So that means in order to slow down, our acceleration has to be negative. So, plus negative. So this is going to be 120 is equal to, negative 120 is equal to negative 4 times change in time. Divide by negative 4, divide by negative 4, change in time is equal to 30 seconds. There you go. And that's part A. Now, part B, through how many revolutions does the disk rotate during that time? All right. Revolutions during that time. So let's convert this all to revolutions. 120 radians over seconds times 1 rep divided by 2 pi. This is equal to 120 divided by 2 pi rev per second. All right. Do the same for this. This is negative 4 rad over second squared. 1 rev, 2 pi. This is going to be negative 2 pi over a rev per second squared. And 30 seconds should be the exact same thing. Okay. So now let's find change in theta for with our new givens. 120 over 2 pi times 30 plus 1/2 negative 2 pi times 30 squared. So I'm gonna keep the 2 pi in as much as possible. So 120 divided by 2, 60 times 30. This is gonna be 1,800 pi. Negative times 900. Negative 900 pi, which is just going to be 900 pi. Hold up. I messed up somewhere around here. Hold up, sorry. 120 divided by 2 pi times 30. Negative 2 pi over 2 times 30 squared. Yeah, I messed up somewhere here. Sorry, guys. Let me take a moment to figure out how to do this correctly. Oh. I don't know where I messed up. I'm way too tired to figure it out, but I'm actually gonna do this in a way easier way. I'm probably just gonna edit that part out. Anyways, remember that our change in theta equation is equal to omega I times change in time plus 1/2 alpha times change in time squared, and omega I is 120, right? Yeah, and our change in time, we just figured that out, plus 1/2, and our alpha is -4, and our change in time is 30 squared. So 3 times 12, that is 36, times 100, 3,600, plus -2 times 900, negative 1,800. This is just going to equal 1,800. And then, so this is a 1,800 radians for change in theta, but we want it in revolutions. So 1,800 rad over 1, we're going to change this into revolutions, is going to be 1 rev divided by 2 pi rad. And 1,800 divided by 2 pi is going to equal 286.479 reps. And we did it. Good job, guys. That is it. That was the entire week in recap. I hope you guys enjoyed, and I'll see you guys next time. Goodbye.